Everybody, I know it's been kind of crazy. I also know that there have been some questions on question 5 and 6 of our gases worksheet 2. So I wanted to go over 5 and 6 because these are kind of trickier problems. I know it's very easy to kind of get lost and sidetracked, so I am going to go over that with you just so we have everything clear. Now, what I'm going to immediately start off with is more often than not, students are going to assume that, we've been talking about ideal gas laws, we've been talking about the gas laws that we can use, and so my initial reaction is to immediately think P1 V1 equals P2 V2. Now, the reason we can't do that is because, first of all, we're dealing with partial and total pressure. So we're dealing with our partial pressure equation, which I'm going to label because we're trying to find dry oxygen. So I'm going to put PO2 equals our molar fraction of O2 over times the P total. Sorry, little t. So we're using partial pressures. Because this sample of oxygen collected over water is technically O2 plus water vapor. So it's a total pressure versus a partial pressure question. And on top of that, the only reason we can use this is if moles, our N value, and our temperature value are constant. And in this case, they aren't constant because we're having a different amount of moles. You're going to have a different amount of moles of O2 plus water vapor versus just O2. And we're trying to find just O2. So what I'm going to say is technically our molar fraction is going to be equal to our partial pressure, which is our PO2, over our total pressure equals our molar fraction, which our molar fraction of O2 is just equal to the mole N of O2 over the NO2 plus the N of our water vapor. I hope we kind of understand this. So from there, we kind of have this direct proportionality. And we have a proportionality in the sense that we can technically make it so that our volume is this case, is our moles, because our moles can only be contained within a certain volume. So we can technically make it to where our equation is the same thing as partial pressure, our pressure of our O2 versus our pressure total, equals, and we can instead have the volume of our total, our volume of our partial, which is our O2, what we're trying to find, this is what we're trying to find, over our V total, which our V total is this, I'm going to put it in pink because I like pink, is this value right here. So now we technically have almost all our values. The last thing we need to do is we need to find our this pressure, because this is our total. This is PT. This is our V total. And we just need to find our partial, which our partial, we're going to subtract our total pressure, which is 764, minus our 30 torr of our water vapor. So that's going to give us around, or actually exactly, 734 torr. So now we have all of our variables. We can plug them in. And so we have our partial, which is 734 torr, over our total, which is 764 torr, is equal to our V of O2 over our V total, which is 0.560 liters. So from here, we can actually do something that if you've taken an algebra class or if you've done mathematics, you can technically do this with an equality. It is what I like to call the butterfly method, where we multiply the top and the bottom, set them equal to each other, and divide what we want out. So we will get let's see, 734 times 0.560, and then we will get 411.04 divided by our 764. And we should get 0.538 liters. I also want us to see here that we technically have torr and liters divided by torr. So we'll have torr times liters divided by torr to get liters. So our units actually end up canceling out because we're trying to find this liters by itself. You see? So that's question 5. Now, for question 6, I can totally understand how this would be really frustrating and kind of out of nowhere because we're not going to use that same proportionality anymore. So we have the volume of oxygen collected at 24 degrees Celsius and atmospheric pressure of 762 milligrams of mercury is 128 milliliters. We calculate the mass in grams of oxygen gas obtained, and the pressure we are given based off of water vapor. Now, I'm not going to lie to you, this is a very kind of silly moment, because if we took this pressure and found the partial pressure, because what we're really doing is we're using our ideal gas law, which our ideal gas law is pressure times volume equals our moles times our R times our temperature. That's our ideal. We're actually going to even go a step further and say that it's technically let's actually just erase this and make it N equals PV over RT. And that's how we would get the moles. I want us to understand that we are calculating the mass of grams given the volume of oxygen collected at a certain temperature and stuff like that. But we're trying to find specifically oxygen gas, and we have water vapor inside this oxygen collected. So it's going to be very similar in the sense that we have a partial pressure and a total pressure. When it comes to ideal gas law, we can do one of two things. We can calculate the pressure total over the partial volume, or we can do vice versa, where we do the partial pressure over the total volume. Me personally, what I would do is I would find our partial pressure and use that with our total volume. So I would do our partial pressure, which is technically 762 minus 22.4. That equals 740 mmHg. And that 740 needs to actually be converted to atmospheres. I'm going to change it to atmospheres right now. It technically equals 0.97 I'm going to round it up to 4 atmospheres. Reason I'm doing that is because it needs to be in atmospheres for the ideal gas law. So we have our atmospheres. This is our total volume. I'm just going to reuse that. It's technically 0.128 liters. So I'm going to reuse that. Our R is going to be 0.08206, and that's our R constant, which is technically liters times atmospheres over moles times Kelvin. And then lastly, our temperature in Kelvin. We're going to use this same temperature, 24 degrees Celsius, and convert it into Kelvin. So that is 273.15 plus 24. That's going to equal 297.15. And so now we'll plug everything in. I just want to reiterate that the reason we're doing partial pressure versus volume total is because we want to account for specifically the pressure or the calculated mass of oxygen gas. We don't want to go super in depth to where we have the total pressure and the total volume, because that's not going over the oxygen gas specifically. That's going over the oxygen plus the water vapor that is inside whatever volume, whatever canister we have. So we have to simplify it down to where we only have a full pressure and partially what our oxygen is. Like if our oxygen is a smaller volume, we use that. Or we'll use the smaller pressure in the total volume that it's in. Reason we can't use partial pressure and partial volume is because at that point you have like double dipped. You have made a partial oxygen in a partial container, which that's not true. The amount of oxygen that we have obtained is inside that same volume that the total oxygen is inside. So that's why we're not going to do 2 partials. We're doing 1 partial and 1 total. Hopefully that makes sense. I hope it did. So we're going to plug everything in. So we have our partial of 0.974 atmospheres times our 28 liters over 0.08206. That's our R constant. I'm not going to write out the whole units because they're just going to cancel out to moles anyway. And then our Kelvin, 297.15. So if we multiply that all out, then 0.8206 times 297.15. We'll have this divided by this. Ooh, something went wrong here. Oh, I missed a 0. That's why. I was really confused for a second there. Okay. This divided by this. We should get approximately 0.00511, and I'm going to round it to 3 moles. Now we also need to multiply this by our molar mass, which O2 is just 32 grams per mole. And so that should equal approximately 0.164 grams of O2. If you have, which I'm pretty sure Deborah has already published these, but if you have the answer sheet to this problem, she does have a note on her guide that says the answer to the problem should be 0.164. If you don't have the correct volume of O2, depending on the level of precision desired, you can get away with using the 1.28 milliliters as the volume for this problem. I believe that this, explanation is not the right one that I would use. Specifically the fact that, as I said before, reiterating that the pressure and volumes are supposed to go hand in hand, in the sense that we're only getting partial pressure because we're only finding partial of the total. And the total is the gas, the oxygen, plus water vapor. So we're only taking a partial even though it is part of the total volume. And vice versa. If we're taking the total pressure, we have to find how much volume the specific O2 molecules take up. And if we were going to do that, we would, use this again, the equation from number 5. But I didn't want to confuse you in that sense of doing that and then taking the partial pressure, because that, again, is double dipping. You're getting too far down the chain of having partials. So you're having a partial of a partial, making it super small. And what we want is exactly 0.164 grams of O2. So with that, I hope this video helps. I hope you get a little more clarity in partial pressure and molar ratio, or the mole fraction. The mole fraction. I always mess up mole fraction and mole ratio. But I hope this was a good study source, and I will see you soon.